Okay, so today my presentation is about functional and reactive. And I was kind of peeking over, oops, this won't play, but I was peeking over earlier and I saw a bunch of these drooping heads. I hope I can keep you awake for half an hour because you have coffee break after this. And I talk really fast, and particularly for this talk, I'm going to talk even faster because I got a lot to cover. So even if you keep your eyes closed, keep your ears open, okay? All right. So my name is Preethi. It rhymes with Pee-wee. I continue to be surprised about how many people can't get my name right. So they'll either say like Preethi with the H bolded and font 972, or they'll go Preethi like a cup of tea. It's just Preethi, and if you can get my name right, I'll have a special place in my heart for you. So I was previously a co-founder at an AI startup. Before that, I was an engineer at Coinbase. I was also a partner at Andreessen Horowitz and Goldman Sachs prior to that. And if you know of me, it's probably because you read some blog post I wrote about a year and 9 months ago about why I'm leaving the best job in the world to become a software engineer. It's been a year and 9 months, probably the best decision of my life. And some of the things I nerd out about now that I'm a software engineer are JavaScript and the web. So JavaScript was really the gateway drug into programming for me. I'm obsessed with functional programming and very passionate about it. I'm also recently learning, teaching myself natural language processing and kind of machine learning because I'm very interested in that space. And I was probably the only middle school student in your middle school and elementary school that liked their phys ed class because I'm obsessed with like fitness and food. So the talking points for today, I'm going to have a quick intro exercise, and then I'm going to talk about the current state of art when it comes to both functional and reactive programming. And then I'm going to talk about functional and reactive combined, and then I'm going to conclude. So how would you describe, oh, interesting, none of the animations will work. It won't play. Oh, nice. Okay. How would you describe this? It's basically a red ball moving in a circle, right? I didn't really hear anyone say, this is a set of frames, and at each second we update the position of the circle. No, you just said it's a red ball moving in a damn circle, right? How would you describe that? You would say it's a box following a mouse position, right? You wouldn't say, okay, you render a square, and at each time that there's a mouse event, you move the box to the X and Y position of the mouse event. No, you just say it's a box following a mouse position. And so how would you actually describe the mouse position? One possible situation is you can say it's an X and Y, right? It's an X and Y coordinate. That works, but that only works for one point in time, right? How would you describe the mouse position as it changes over time? Maybe it's an infinite list of X and Y positions for every time the mouse position changes. Or maybe it's even a stream of mouse positions, right? So really what this is what the mouse position is it's a function. It's actually a function in time, because every point in time, this mouse does have a position. And that's really the essence of what functional reactive programming is and what I'll be talking about in the second part. But I wanted to give you a glimpse of that in the first part. So the kind of premise is that as programmers, we're so used to describing how things work instead of the what. So the things we have to deal with a lot of low-level details that have nothing to do with the actual desired content, but actually about how to get the computer to present that content. And so things like, for example, motion and growth, these are very gradual and continuous phenomena. But since computers work in very discrete steps, they can only do one thing at a time. What we as front-end programmers and graphics programmers have spent a lot of our time doing is kind of bridging the gap between what an animation or UI is and how to actually get the computer to present it on a computer. And so now that we have much more powerful abstractions and much more powerful computers, how can we get to a place where we simply just describe what an animation is and not how to render it on the screen, right? And that's kind of what we're moving to in the current front end. So the current state of art is really helping us move in this direction. So for example, with React, what React gives you is a very declarative way to declare your components. Maybe 2 years ago, this is how your component code would look, right? It's very imperative. The DOM exists as an in-memory representation of your UI, and you kind of poke at it to make changes. Whereas with React, you have a much more declarative way of just telling it what you want it to render, and it will render it for you. Similarly, React also gives you purity, right? You can take the same button component and now wrap it in a pure component that simply accepts props and renders the button based on those props. And then now, all of a sudden, your components just become as easy to test as any pure function. You just pass it whatever state you want and just test the output. Incredibly powerful. And similarly, React also, because of its compositional nature, it kind of encourages you to reuse your components. And not only that, because it's compositional, as Nick Graff talked about earlier, it kind of promotes this idea of compositionality and higher order components, right? So a higher order component is just a function that takes a component and returns a new component that's enhanced with certain features and functionality. And the compositionality like this is very powerful because now we can reuse component logic. And then you have stuff like Redux. So what Redux really did for the front end was it kind of popularized this idea of immutability. So in Redux, we know the state is read-only, right? And to update state, you never mutate it directly. Instead, you use these pure reducers, which take the current state, clone it, and apply the changes, and return the new state object. And the reason that Redux really, really harps on this idea of immutability is because it's trying to get purity. Purity for a majority of your code base. So, for example, even your actions are pure. Instead of event meters, you use pure actions to define some kind of change event. And then to actually handle a change, it's also another pure function, as we saw earlier, where we just return a new state object and it's immutable. And so by putting a lot of your logic on the pure side, Redux gives you the benefits of purity, which are like, A, it's very predictable. It's very easy to test, because nothing is easier to test than side effect-free functions. It's very composable as well. For example, with reducers, we can control the order in which they're called. We can pass additional data. We can basically reuse reducers for common tasks. You can build more complex reducers out of smaller reducers. So by having a lot of your code be on the pure side, you get a lot of the benefits of pure functions. And then you have something like RxJS. So RxJS you can think of as basically Lodash for events. And for those of you who might not be familiar with it or have not used it, there's basically 4 concepts with RxJS. So RxJS has this concept of an observable, which are lazy push collection of future values or events. And then it has an observer, which listens to the values delivered by that observable. And then a subscription, which is the execution of that observable. And then you have a bunch of operators like map, filter, and concat, which are pure functions that enable you to use a functional programming style to deal with these collections of events or future values. And so what RxJS really brings to the front end is reactivity. So let's say you have a button, right? And then now, all of a sudden, you can create an observable from the clicks to that button. And then when you want to get the values out, you subscribe to it, and you're called back with each value in turn. And so your program is now expressed as a reaction to its inputs. And similarly, RxJS also gives you a very declarative way of handling your event logic. So let's say you want to count the number of clicks with the throttle rate of 1 second. If you didn't have this declarative way, you might have a counter. You might keep track of how many clicks with various counters and variables, and you might have listeners, and this is how you might define your logic. But with RxJS, you can just say, okay, from this button click event, I want you to wait with a throttle time of 1 second, scan for the count, increment the count, and then subscribe to that count. So it's very declarative. I'm just telling it what I want instead of telling it and setting, updating, and checking counters and telling the program how I want it. RxJS, as you can already probably see, allows you to use higher order functions on your events as well. So another example is, let's say you have a stock price stream that's coming from some website, and then you have other functions like format money that just formats your money, and then above price threshold, which checks if a number is above certain threshold before you can buy it. So now what you can do is you can say, okay, I'm going to subscribe to that stock price. I'm going to pluck the price property out of that. I'm going to filter for the ones that are above a certain threshold. I'm going to map it to format the money, and then I'm going to subscribe to those prices. So what happens is, instead of processing each individual event, what we're doing is we're creating a stream of these events and applying higher order functions on those events. So really, we can visualize our system now as basically data pipelines that are connecting publishers to subscribers, and then we're applying higher order functions on that data pipeline. Very powerful, and something that functional programming obviously really preaches on, this idea of higher order functions. And then we have Mobx. So Michael talked about it, I think, in the first presentation today. Mobx also brings a powerful idea of reactivity to the front end. So as you probably already know, Mobx adds observable capabilities to existing data structures like arrays, objects, and so forth. So you kind of define your state as observables like this. And then what Mobx does is it'll observe references. And anytime that property is dereferenced or dotted into in a tracked function, Mobx will record it. So, and then if that reference is changed, Mobx will automatically react. So let's say we have that same user object in our observable, and then it also has this idea of computed values, which are derived from the current observable state using a pure function. And the power of this is that Mobx handles keeping track of when these computed values change, and will handle the updates to these collections automatically. And how it does this is it builds a graph of all your derivations in your application to find the least number of recomputations. So it's also super efficient. And it's a lot more efficient than you writing your own event handling logic or you using like smart selector-based container components, because what Mobx is able to do is kind of establish much more finer grained control, which is, I think, what Michael talked about earlier. And then you take it a step further, and you use now this observable state in your React apps. And now, if you wrap your React apps in an observable decorator, now your React components are efficiently reactive, meaning that Mobx will force a re-render only once the data that's used in the render function is changed. So it's very efficient. So kind of to summarize, what the current tools have gifted us with are we're moving from a much more observer pattern with listeners to much more reactive patterns. We're moving from imperative to declarative, from stateful to stateless, and from object-oriented to functional. And the reason we're doing this is because we see a lot of the benefits, right? So for example, with purity and referential transparency, we get predictability, we get composability, we get something that's easy to understand, easy to test, easy to refactor. And then similarly with Mobx.js and RxJS, they really help fix listeners in a huge way, right? Listeners can be pretty painful to work with. Like they can have unpredictable order, you might miss the first event, you have super messy callback soup, you can have leaking callbacks. I think RxJS and Mobx have a powerful way of fixing that. They also kind of create this idea of dynamic or continuous values. So you subscribe to it once, or you define your relationships once, and those values are up to date automatically for you. And then you think of your data in terms of flows of data instead of flow of control. But what's in one is not in the other, right? So React and Redux have that functional part to it, but they don't have the idea of dynamic and continuous values. Whereas like Mobx and RxJS, they create this reactive, dynamic, and continuous values, but they don't really enforce referential transparency like Redux does. So how can we get the best of both worlds, right? And functional reactive programming, we'll see how it combines the principles of both functional and reactive programming in a powerful way. But I'm not saying it's the answer. I'm saying it's probably one of the many answers. So what is functional reactive programming? It took me a while to click and really understand what it is. So I'm going to throw a few definitions at you, and maybe you'll walk away with some understanding. But there's no way I can teach you functional reactive programming in 15 minutes. But I'll get you the gist of it. So basically, functional reactive programming is reactive programming that enforces the rules of functional programming, particularly the property of compositionality. Take two. Functional reactive programming is about data types that represent a value over time, so an evolving value. In conventional imperative programming, you can only capture evolving values indirectly through like state and mutations. Whereas in functional reactive programming, you capture those evolving values directly, and it has no difficulty with continuously evolving values. Take three. It's all about describing a system in terms of time-varying functions instead of mutable state. So really, The essence of functional reactive programming is about specifying the dynamic behavior of a value completely at the time of declaration. And I'll show you what this means in more code, but as an example, let's say you have an X and Y mouse position, you'd make this assignment once, and those values would be automatically up to date. So the basics. You always start with some kind of event. Something happens in your code that propagates from one part of the program to another, right? This can be an input, this can be a click, this can be a submit button, and so forth. And there's two main concepts to understand. There's streams and there's cells. Streams represent a stream of discrete events. These can be mouse clicks, these can be connection to a server being established, this can be shots being fired at a game character, and so forth. Then you have cells. Cells represent a continuous value over time. And the key thing to understand with cells is that you have to declare the update logic at the time of declaration. And the update logic can specify two things. It can specify the event streams which affect that cell's state, and then the operations that will handle how to handle those event streams on the state. So things that you can model as cells are like position of a mouse, text input value, and so forth. And then you have operations. So operation is a function that that converts streams or cells into other streams or cells. And there's 10 basic ones: map, filter, merge, and so forth. These are kind of like the higher order functions we saw before. So I'm going to give you a conceptual understanding of it through diagrams, and then I'll show you a few code examples, and I'll kind of conclude. So let's say you have a travel booking interface, right? And the business logic for that is if the departure date is less than or equal to arrival date, it's a valid search. Otherwise, it's not a valid search. And so the user enters these dates into these two date fields, and that flows into some business logic, and that flows into the search button. That's the essence of functional reactive programming. But what do I mean, right? So if for those who are thinking code, I'm using a library called Kasireddy.js that implements FRP and JavaScript. It works for demo purposes. It's definitely not production ready or anything. But basically, you would have two date fields, and then you have a search button that accepts an is valid variable. And the main thing to get here is this is valid variable, which is a cell. Again, a cell is a value that changes over time. And how we define that cell is that we're saying it's a departure date, the current departure date, the current arrival date, and we're comparing whether the departure date is less than or equal to arrival date. And we declare all the logic up front, and we never reassign the cell again. So again, a cell is a container for the value that changes over time. So taking this is valid example, maybe it starts off with true, and then at some point in time, it still stays true. And then the user does something, and it becomes false. And the user does something, it becomes true. But no matter what time we sample this value, it will always have a value, and it'll always be up to date. So the core thing to get with functional reactive programming is that we're representing dependencies as relationships. So you're seeing that these arrows show the flow of data from two dates through some logic and into the search button. And as the user changes the dates, the search button will be enabled or disabled dynamically. And it's really the FRP engine's job to know all these relationships and not you as the programmer. So how does the FRP engine work? So what happens is you write a bunch of FRP code, and then during the initialization stage, what happens is it creates a directed graph in memory based on the code statements that you wrote. And then now it's the FRP's engine's job to derive the execution order automatically from this graph. And so during the running phase of the program, if there's inputs, it's the FRP's engine's job to maintain the relationship that we expressed in our code. And so it will ensure that things are processed in the right order, specified by the dependencies, based on the directed graph it built. So let's compare this idea of representing dependencies as relationships versus how we would typically do it. Typically, what we would do is we would reverse the data flow. So we would say, search depends on arrival and departure. And so in that case, we might say, we might have some function that updates the search button based on our business logic. And then we'd have some event listener that listens for input values on those date fields, and then it first updates the departure date, and then it updates the search button. Same thing for arrival date. The problem with representing dependencies as a sequence comes when you go to change the code, To make something happen earlier or later, you need to actually make sure you fully understand the dependencies that are implicit in the sequence, right? Whereas FRP, you kind of express those dependencies directly. And so you can just add or remove the dependencies, and the sequence will be handled for you automatically. Whereas with regular listener-based handling, you have to manage that sequence yourself. And so the core thing to take away is that with FRP, you're staying at the level of the relationships between things and not the mechanics of their interaction. So I'm going to go into one example of a cell and one example of a stream in more code. So let's say you have two text inputs and a label. And the label is determined by the values in those text inputs. So because these text inputs are values that change over time, I'm going to model those as cells. I'm going to say a cell A is whatever value is in that text input. I'm parsing the integer out of that and defining that as cell A, and same with cell B. And then I'm saying the output is the current value of A and the current value of B, the sum of those two. And now I declare this logic once, and that's it. The values are up to date throughout the test of time. Notice how I'm not saying on input update, first update this value, then add the sum. I'm just kind of declaring it all at once. Then for a stream, let's say you have some quantity that you're trying to model in your state, and maybe this quantity represents the number of products that a user can buy or add to a shopping cart. And then you have two buttons, add or subtract, where they can add or subtract the quantity. And then what you might do is you might model the delta in the quantity as a stream. So anytime the add button is clicked, I'm mapping that to a 1. Anytime a subtract button is clicked, I'm mapping that to a -1. And then I'm having another stream where I take, anytime that delta stream is fired, I'm saying snapshot that delta with the current quantity, add the delta to the current quantity, and give me the updated quantity. And then filter for the ones that are greater than 0, so because you can't buy negative quantities. And then finally, you update the quantity with the updated quantity. So this is all I have to do with define all the logic, and I never have to worry about the sequence or the order or anything. I just define the relationships, and the FRP engine takes care of everything else for me. So if you want to kind of see a diagram of the flow, this is how it's kind of flowing. And the main thing to get away from this slide is that a stream only has an event when something fires, whereas a cell will always have a value, and it'll have a value that's up to date. So in this case, the quantity cell might start with 1, and then after this transaction happens, it'll have a value of 2. But a stream will only have a value when that stream actually fires. So this stream will only have a plus value when it fired, this stream will only have a 1 when it fired, and this stream will only have a 2 when it's fired. So kind of double clicking on this point, as I said, cells always have a value that can be sampled at any time, whereas a stream doesn't. Stream only has values when it fires. So you can think of a cell as having memory, or you can basically say it is memory. And if in traditional FRP, cell values are actually modified in place. So it's actually a non-local mutable variable. But didn't we just say how mutability is terrible because it breaks referential transparency and all that? And yes, that's very true. What FRP does is it basically takes the evil out of it by wrapping it in this evil-proof box. So even though the value inside is mutable, the container itself, like the cell itself, is not mutable. It's immutable. So you can still use it in referentially transparent functions. So it still allows you to use composition in a very powerful way. So to summarize, cells, they don't initiate change, streams do. Cells are passive, and streams are active. Cells have memory, streams have no memory. And then cells model state, and then streams model state changes. There's a lot more to learn with FRP. There's no way I'm going to get through it, but I'm happy to share this deck with you in terms of what are the other things to learn. But I kind of want to talk about why I really fell in love with this idea. And obviously, one thing is it's very declarative. But two, the big thing is it solves a sequence problem, right? Typically, we've thought about programs sequentially. But with cells, they solve that problem because with values over time, dependencies don't really need a sequence. Because they automatically come with an update notification and sequence management. And so the state is always up to date automatically for you as a programmer. And third, because they really enforce referential transparency. So what if we can kind of take these ideas of functional reactive programming and make it work for us on the front end, right? What if we can take this powerful idea of a cell and model it such that it's observable reactive state with update logic that's defined at the time of declaration? And you can think of this cell much like a Redux reducer in the sense that it entirely depends on the reducer for the update logic. But the cell would also be very much like a Mobx observable, because now you can react to its state changes. But the difference is that, unlike Mobx observables, you wouldn't be able to set the value of these cells directly. You have to define the entire update logic at the time of declaration. So we'd be combining the benefits of Redux-like functional programming with Mobx-like tracking and observables. And the advantage I see in something like this is that with React rendering, you can get much more finer-grained subscription, as Michael was showing earlier, because we can model it such that individual properties are tracked automatically, and we would build a graph of all the derivations so that the computations to the dependencies are automatically tracked and updated. And if we also have a graph of all our derivations, now we have much more efficient recomputations as well, similar to Mobx. And some people might say, well, with Redux, you can also subscribe to state changes. And that's true, you can do that. But with Redux, since state is immutable, you'll have to perform shallow comparisons, which is what React Redux does. Or with dynamic collections like arrays, you have to normalize the state tree to avoid unnecessary reconciliations. And so I think by defining our relationships in this way, we can ensure that the relationships are still like insensible to time, and they won't be affected by the outside world. Yet at the same time, we can take advantage of the power that you get from like observable, dynamic, and trackable values. And sure, maybe the values in the cells are mutable, but frankly, I don't really care about immutability at this level, because the whole purpose of immutability in functional programming is really to get referential transparency with values that can be mutated over time. So even though the values within these cells are mutable, if you can ensure that we encapsulate this mutation in a box, and we only mutate the object through like a stream or action which is still pure, and the update logic is strict enough so that it can't be affected by the outside world, it still means it's predictable, it's composable, it's testable, and all the other advantages that come from referential transparency. So really, our goal isn't immutability for the sake of immutability. It's immutability because we've wanted referential transparency. So why do we even care about referential transparency, right? Like, why do I keep saying I love referential transparency or I want referential transparency? And the reason is because it allows for compositionality. You can't really guarantee compositionality if you don't have referential transparency. And compositionality is when basically we take small, reusable, independent functions or modules and build bigger programs out of that. And rather than thinking of new functionality as like adding and extending methods to classes like we do in object-oriented programming, compositionality allows us to create new functions and new modules and use composition to tie them together. And as a program gets larger and larger, more and more complex, I think compositionality becomes more and more important. And particularly on the front end, we're seeing that our programs are not getting any less complex. They're only getting more and more complex. We have to deal with more and more types of state. And so if you can think about compositionality as a way to deal with that complexity, it becomes very powerful. And something I've observed from being part of functional programming communities is that they know from experience that functional programming deals with complexity better. But when you ask them, they can't really point the finger on why, and I truly believe it's because of compositionality. Functional programming works because it's compositional. And so I think compositionality is really the missing element that we need to be talking about more in the front end, and that's why to get compositionality is the reason we're seeking referential transparency in the first place. So I'm going to add one more bullet to why I love FRP, and it's because it deals with complexity via compositionality. So if FRP is so powerful, why hasn't it taken off, right? Like if I'm raving about this concept, why hasn't it taken off? And I don't know, one reason might be it might not make sense for all cases. This directed graph workflow, I know it works really well for games and interactive visualizations, but I personally haven't yet tried it for CRUD apps, and that's my next step, but maybe it doesn't make sense for all applications. Or maybe the current FRP APIs are just too hard to use in the front end. Maybe they're not very practical. But really, I think the true reason is inertia. Like as programmers, we're taught state, we're taught mutation, we're taught object-oriented JavaScript. And just now, we're getting introduced to the power of functional and reactive programming. And these kinds of mindsets aren't going to change overnight. And I'm actually pretty impressed by how fast people are moving towards these paradigms in the front end. And in fact, like, it's pretty exciting. And my goal, and along with the community's goal, is to kind of push these ideas forward. And maybe this is the time when functional programming finally takes off, because people have been saying that for like 30 years, and it hasn't ever taken off. So closing thoughts, your primary goal as a developer is to manage complexity. And the beauty of being a JavaScript developer, I think, is that you have choices. So if you want to use functional programming, use functional programming. If you want to use reactive programming, use reactive programming. If you like some of the functional reactive ideas, use that. Or if you want to stick to your object-oriented ways, go for it. So choose a solution that works for you, and invent new ones if you see the need. All right, now you can have your coffee.